Okay, hi everyone. My name is Dhruva Chakravarti. I hope I'm not blocking anyone. I am a researcher at HP Labs. And what I'm going to do today is kind of set up the context with what we are calling the machine that we're building at HP. It's a convergence of a few technologies, memristor-based non-volatile memory, and I'll talk more about that. Lots and lots of cores, and also very fast interconnect. So it's a machine kind of to do maybe things that you do today, but much faster, but also hopefully new classes of applications. Now, what is kind of more relevant for folks here, I thought, it was how would you program something with non-volatile memory, with persistent memory, and that's what I'm going to focus on today. So we have Atlas, which is a programming model, a system that we have today. We have an implementation model and design. It's not yet open source. We are planning to open source it very soon, so hopefully pretty soon you can kind of play around with it, but not today. So, but I wanted to spend time about, a lot of time on the design, the motivation, what exactly we're trying to achieve, and why kind of it's a differentiator going forward, or this class of programming, why it is something we need to pay attention to. Okay, so let's set the context a little bit. Why do we want it? Like now, this is kind of the canonical big data slide, where if you think about what we have today, there's a lot of data getting produced all the time. There's so much that we can't even sort of forget processing, even kind of, we can't even store all the data. And we are not able to really analyze it, not able to secure it, and so on. So the question is, if we had some technology which would let us do that, what kind of actionable intelligence would this give us? And real-time insight, and so on. So it turns out that if you have non-volatile memory, then maybe you can get closer to this. So what is non-volatile memory? So as you know, as feature sizes are shrinking, DRAM scalability is becoming more and more challenging. And this has been going on for a few years now. Now, if you look at alternative technologies, alternative memory technologies, memristors, phase change memory, spin-talk transfer RAM, and so on, they give you kind of the best of DRAM and hard disks. So they are byte addressable, meaning that just like today, you do CPU loads and stores, and you can access the data that you have in non-volatile memory. So it doesn't matter which technology. There are differences in when you consider the specific technologies, but you can access all of them using CPU loads and stores. So just the access pattern that we are used to today for in-memory computing. They're also persistent, which means that if you, in contrast to what you have to do with DRAM, with these non-volatile memory technologies, if you store data into them using, let's say, a CPU store, turn off the power, come back later on, turn off the power back on, and that data is still there. So that's a major differentiator compared to what we have today. The question is, can we take advantage of that? What would it take in the programming model to take advantage of that? So, and again, like I said, depending on the exact technology, latencies differ, but we are talking about pretty low latencies comparable to what you have with DRAM, tens to hundreds of nanoseconds. It depends on the exact technology, and it's a moving target. So we think that in the next 3 to 5 years, these technologies will get to a point where you're going to get pretty low latencies and also high bandwidth. Retention is pretty good. There are some endurance issues like we have today with Flash, but the endurance issues are much less than what we have today with Flash. And again, it depends what technology you're really talking about. So the point to note is that there are two things that it really gives you from at least the programming standpoint: load, store access, and persistence. And this kind of gives us probably an opportunity to say, well, could this be universal memory? Does this kind of this is the hierarchy that we are used to. Now, could it flatten the hierarchy? So do you need all of these levels that you have? And this is kind of really thinking far ahead, but at least what it gives you the potential to persist data not necessarily on block devices like you do today, but in memory. So you store into memory, and the data will be there regardless of failures and crashes and so on. So given this, what we would like to do is, if we are to take full advantage of this, that in-memory durability. So you store data using just your objects and loads and stores, and basically your data is persistent. So I think maybe, yeah. So let's first talk about what you have to do today. By the way, I'd like and for this talk to be interactive, so if you have questions, feel free to ask. Stop me at any point of time if you have questions. So let's talk about what we do today if you want some data to be persistent. You typically have an object format of your data. That's what your algorithm processes. That's what you are manipulating, creating, updating, and so on. But from time to time, you say, oh, okay, now I have to write it to a block device, a hard disk, let's say. So you have this separate format, the file format or the database format. So first you have two formats of data. And then when you need to write out, basically there's a serialization, deserialization phase where you say, okay, now I have to write out, let's convert, let's have a translation, and so there is a translation layer involved. And the moment a translation layer is involved, you are paying performance costs, and also there is a usability issue. So just to be clear, I mean, there will be file systems and databases, no question about that. But in this new world, what we have started exploring is whether there is also a more direct way to getting to persistent data. And file systems, databases do give you lots of properties that you need, and they're very important. And there is quite a bit of work going on trying to optimize file systems and databases for non-volatile memory. But this talk is more about how do we open up persistence to everyone, not just programs which are going through file systems databases. I like to think about it as how do we open up persistence to all the world's programmers. So let's go back to the previous slide a little bit more and talk about that a little bit more, that this is kind of the architectural model that you need to have. So there is the CPU, there are still transient caches, there will still be a little bit of DRAM potentially, at least in the near term, and then there'll be non-volatile memory. So if you think about it, yeah, we will have non-volatile memory, but that is still not the complete picture. There will still be buffers and structures which are transient.
So the question will code in this case, will we start executing code from without loading it into memory? So you execute in place? Is that
so if I understand your question, you're saying in this new world, can we restart execution without loading it to memory? Well, yeah. We are kind of positioning, when you say memory, you mean DRAM, right?
Yeah.
Yeah, so that's correct. So like the picture shows, we are positioning non-volatile memory as memory on the system bus, side by side with DRAM. One day, hopefully, it'll replace all of DRAM, who knows? So it is still memory. So, but you're right, we don't have to buffer in DRAM today, like we do today. Unlike we do today. So this I already talked about, that you now have objects, and the difference is that they're durable. So you have a single format of data in contrast to what we have to do today. So potentially there is a big programming benefit, big usability benefit. You don't have to think about whatever format you use for the file system databases, object relational. There's a lot of kind of grunt work that we have to do today when we want persistence. You don't need to do that. So there clearly is a kind of model change and rethinking that you need to do. So if you had that, and that's the model this talk is after, that, okay, you have objects and they're persistent. What possibly are some of the abstractions? And so here what I have is what we're calling a persistent region or a persistent heap. So this is a container for your persistent data. It could be objects, It could be references, pointers, what have you. Now, I've shown some pointers there. They could be native pointers, they could be relative pointers, fat pointers, whatever. But basically, these are the containers of your persistent objects. You can have many of them, and you can think of these as memory mapped files. So, in fact, we are implementing today, you are using memory mapped files. We are also saying that it should probably have a root, which means that as a programmer, you create a persistent object, you allocate data structures out of it, like objects and so on, and then you make sure they're accessible from the root. And why do we want that? Because if you think about it, memory leaks are pretty bad today. And in this world of persistent memory, memory leak is even worse because they're kind of persistent memory leaks. And persistent memory leaked by one process might start affecting another process. So it seems like that we need to have kind of more sort of first-class support for stuff like garbage collection and so on, whatever be the environment you're dealing with. So the root kind of is motivated by at least a couple of things. One is, and I'll talk more about this notion of persist and reuse, but the idea is that if you have persistent memory and your objects are persistent, you should be able to just go restart your program and reach out into the existing data. So the root or roots, if there are multiple of them, are kind of the gateways, the entry points to the data that you have in your persistent region. So by starting from the roots, you can get access to the data that exists already. And they also give you a way to garbage collect. So the invariant that we have in our model is at program termination, normal or abnormal, any data that is not reachable from any of the roots of persistent region, any data within a persistent region that's not reachable from one of its roots can be considered garbage by the system and reclaimed. So that's kind of the notion. We would like to have garbage collection as a first-class citizen. So anyway, going back to a persistent region, so you could have multiple of these, and if you think about what we do today, we may have data structures that we want to persist, but then there are also data structures that we really don't want to persist or we don't care about their persistence. So we also have this notion of transient data structures. They may live in non-volatile memory, but logically they're transient. So anything outside these persistent regions, that's considered transient. So you, as a programmer, can identify the data that you want persisted. And if you do not identify something specifically as being persistent, they will be considered transient. So this is also kind of trying to keep sort of backward compatibility with what people do today. If you write legacy code, there'll be minimum changes required for transitioning from your existing code to something that makes use of persistent memory. Now, on the right-hand side, this is kind of a little bit descriptive API, but this is pretty much what you want to do. And don't pay too much attention to the names. They're supposed to be descriptive so that it's easier to understand. So like I said earlier, these are named containers. So you should be able to, so you kind of have a finder in your system where you should be able to say, okay, given this is a name that I have and I know what data I should have, is there data corresponding to this? So you can say, okay, find this region. And then because we have a root, you can go ahead and check whether there is any data in it. If there is already existing data in your persistent region, you should be able to go ahead and reuse it and kind of get closer to what we have been trying for a while, like instant restarts, immediate restarts, and so on. So this is kind of the relevant code. So we are doing a find, and then we access the root pointer, and if there is no data, so let's say this is the first time you are starting up your process or your application, so you'd pretty much do what you do similar today, that you'd allocate some data structures and make sure that they're reachable from the root pointer. So you set the root pointer to point to that, so that after process termination, the system doesn't garbage collect your data. So that's something you have to do. But if you do find there some data, you'd want to reuse them. And this section of the code basically are your algorithms. So this is kind of standard boilerplate code that you potentially have to add probably at the outset of your program, where you find yourself in the context of persistent data if something already exists. And the rest of your program potentially remains unchanged. So hopefully a simple model that will ease the transition from today's programs to ones with persistent memory, taking advantage of persistent memory. And so the idea is that if you look at most programs today, unless you're dealing with server applications which are persisting their data, many of them are stateless. They have no notion of persistence. Now, the question is whether this kind of a model lets you get to kind of persistent versions of those applications in a pretty easy manner. So that's kind of the new class of applications that we would like to enable. Like I said, why not open up the persistence to everyone, to all the world's programmers, not just when you have two different formats of data and go through file systems and databases. Well, so nothing is for free, right? So it turns out that, yeah, you can persist and reuse. That's really what you want to do. But if you cannot keep the data consistent, then it's really not reusable. It looks corrupt. So, and why does it happen? It can happen because of at least two reasons. Like I said, we still have volatile buffers and caches and so on. So let's say your program is executing and you're in the middle of updating your data structures and you're doing CPU loads and stores, and then there's a failure. Now, part of your state are probably caches, and part of your state probably non-volatile memory and maybe DRAM and so on. So when you, let's say the process dies, machine dies, and you recover, you really don't have all the state there. So the trick is to make sure that at any point in time you have enough information in non-volatile memory so that regardless of failures, regardless of crashes and so on, you can always recreate a consistent version of your data structure. So I talked about caches. The other one is, you take the canonical example, the balance transfer example, and and that's the section of code where you're changing your invariants. And if you crash in the middle, then someone is going to be unhappy, right? So what you really want is some form of failure atomicity or all or nothing guarantee. So if you look at that code section again, what you really want is for everything to happen and to make sure that all of those changes do propagate to non-volatile memory. So either because if there's a failure, because you still have transient buffers and structures, that could be one reason why you could have an inconsistent state. The other reason is that you did not finish all the updates. You crashed in the middle, so clearly your invariants are not satisfied. So, so let's take a step back and think about it. We are talking about a slightly new programming paradigm where you have to rethink some of your data structures. So if you have a program today which starts and computes from scratch and goes away and that's all it does, you probably have to rethink which data structures can be persisted and reused, because if there's no reuse, then there's no point in persisting, because in order to keep things consistent, you'd pay a cost. Hopefully not a whole lot, but there is a cost associated with it. So if you don't have to pay the cost, then don't make it persistent. It can stay logically transient. And for data structures that are persistent, you probably have to do something to make sure that the invariants are met regardless of failures and so on. So there is a rethinking, there's a re-architecture of your data structures that needs to happen in order to kind of delineate data structures that can be reused. And those are the ones you want persisted, and also how you keep them consistent. Okay, so I talked about that. So this is how you would look if you don't keep things consistent, right? So if you crash and you're potentially left with holes in your data, you clearly don't want that. Okay, so let's talk a little bit about related work. And people have been looking at this model of programming for a while. So one thing that has been pretty popular and clearly very useful is some kind of transaction support for non-volatile memory, or for persistent data structures. So one is came out of Wisconsin, University of Wisconsin-Madison, mnemosine. So basically they say, okay, we'll give you ACID transactions. They had other things also, but when it comes to the core model and the consistency support, so basically they give you ACID transactions, meaning that if you go back to the section of the code, the balance transfer, you'd want to kind of enclose that code in a transaction, and automatically the system will make sure that you get all or nothing guarantee. So isolation between threads will also be taken care of, and if you fail in the middle, you are going to see either all of the state, well, if you fail in the middle, you're just going to kind of wind you back to the start of the transaction. NVHIPS is another system, came out of UCSD. They had similar transactional support. Storage Networking Industrial Association, they have a non-volatile memory programming working group where they have been talking about this programming model that, okay, you now have persistent memory, you can use them using CPU, manipulate them using CPU loads and stores. What are the kind of APIs and use cases that we should do? And they have been talking about some kind of ordering primitives that would let you kind of reason about some of these consistency issues. Non-volatile memory library, the pmem.io project, so that also has been looking at low-level support and also some kind of transactional mechanisms. They do not support kind of ACID transactions, but they do give you failure atomicity of your computation blocks, as long as you also have another way to isolate threads. So, and it turns out if you go back, actually decades, there have been persistent programming languages. People back, I think in early 90s or late 80s, they looked a lot into persistent programming languages and what are the APIs that you want, what are the abstractions that you really want. So the issues were that you still had hard disks. So while the abstraction was nice, all of that was implemented on top of hard disks, so there was a lot of performance overheads that they had to pay. So, and also there were other architectural differences which made things really hard. Now, here there is a major advantage. So we have we are going to have real persistent memory, and the latencies should be low enough that I think we can take this a long way. Okay, so the rest of the talk, I'll kind of focus on some of the work that we're doing at HP to figure out what's a model that we can build to take advantage of persistent memory, and what are the use cases and new classes of applications that we can enact. So some of the things bullets here I mentioned, as a programmer, your first responsibility would be to kind of identify what would be persistent, logically persistent, what would be logically transient. So there are APIs, like I showed you some of it, that you have to say, okay, here is a persistent region that I want to create, and here are the data structures that I'm going to put into my persistent region. So they're the only ones that will be kept persistent by the system. The rest is transient, and there are no guarantees across failures for any transient data structures. Now, the key differentiator that we have here is that you write ordinary multi-threaded code. So transactions are great, and we should have them, but there are also a lot of code that uses some kind of locking mutexes. So we support lock-based code, and as I'm going to show in later slides, that we are able to automatically infer consistency, semantics, and kind of sections of code where you really want, as a programmer, where you really want failure atomicity guarantees, all or nothing guarantees, and so on. So, but at the end of the day, I think all of the techniques that I showed earlier and our technique, they kind of have a common goal, that what you want is persistent data structures directly mappable, like we discussed, not through DRAM, not through any buffers, directly mapped to your address space, directly accessed using CPU loads and stores, and also consistent. So regardless of failures, you can come back to them later on and reuse them.
What do you do with fragmentation then?
Fragmentation, it's kind of going to be something that the memory allocator has to deal with. So like I showed earlier, that you will have some kind of persistent malloc. Now, you could think about kind of bringing in all the technologies that we have in our allocator today and more.
Yeah,
So
today we'll have the fragmentation on file system level will be hidden behind the buffering. So I'm thinking about already fragmented persistent area where you want to allocate large chunk of continuous data. You to try to deliver buffer without us. Unless the persistent area is more like physical memory than mapped via NVM, and you are getting the virtual contiguous memory area on the top. That's just.
So we are talking about large non-volatile memory. That's what this technology really gives you.
However your memory large is, you will still get this to a stage of fragmentation. Then you want to allocate larger amount of memory, contiguous memory, then you have the largest available block.
Right. So there'll be an allocator which needs to look at fragmentation issues.
So hold on, because what the allocator will do, because the thing is that you will be accessing your data directly via pointer, right? Directly with memristors. So you will keep reference to the data somewhere else. You can't just shift it, right?
Well, so
you cannot see the fragment in memory at this stage.
So potentially you can. So if you go back to the persistent region that I showed, and right, so you can have native pointers, then there is some of that issue that you were mentioning. But we can also keep relative pointers, then we can move them around.
That's okay.
Yeah.
If that's what you are managing, that's fine.
Right. Well, there can be different models. So current implementation actually doesn't support relative pointers, the one that we have right now, but we are in the process of incorporating relative pointers as well. And clearly there's a cost to pay. If you're in the C++ environment, then there are funny things that people do all the time, right? Pointer manipulation, so kind of stashing away pointers in hash tables and later retrieving them and dereferencing them. So if you have relative pointers, those become hard. So you probably can't handle arbitrary C applications if you have relative pointers, but you get those other benefits and many other benefits. I mean, because now we have persistent memory and we are saying, okay, we may put critical data now and hope to reuse them later on, we'll probably move them around, so then you need relative pointers.
The bottom line is that you will have to handle the fragmentation case only at the end, right?
Yes. So in a certain way, it's very related to what today's memory allocators need to do. But it's probably a little bit more than that. If you have relative pointers, I think the problem is very similar to what you have today, the allocation from DRAM. So let me take a question at the back.
Well, I guess the comment I just want to make is a little bit deviation, is that you're right. It does become a paradigm shift.
I'm sorry, I missed that.
It does become a paradigm shift.
Okay.
Today,
You want to catch this?
just the way.
That's a great. Hello?
Yeah.
Wow. Okay. All right, so now I don't have to shout. So you're absolutely right. This is a paradigm shift. This is very interesting. And if you think about the way RAM is used today, I mean, we don't have really good allocators, and it sort of doesn't matter. You know, a process dies, you know, it gets restarted. And if you get, you know, coming a bit from an IT environment, you know, nobody runs systems for a long time. Uptime is great, but at the end of the day, it sort of doesn't matter, right?
Yeah.
You know, you go towards these container-like models where, again, you don't have persistent state, so you can bring things down, bring things back up, and it all works because it's all basically extremely volatile, right? And now, when you go back to disk storage, and you know, you consider that, okay, you know, people are trying to figure out decent ways of storing data, and again, you have fragmentation, right? And so fragmentation actually becomes a huge issue in storing data, so you start dealing with like log-based storage, and especially when you run into media, problems with media itself, like flash and all that, you know, you can't just sort of reuse old algorithms. So at least my insight on this is that actually you can't just gloss over and say, well, we'll come up with a better allocator. Unfortunately, this is something that before you really settle down with a programming model, this is something you have to do now. So you mentioned that today you don't deal with relative pointers, right? So you don't
That's
really...
just the implementation. There's nothing in the design that precludes
I mean, that's sort of already a problem, right? I mean, effectively, the kinds of issues you're going to be seeing are the same kind of issues people saw 20 years ago in memory-starved machines. You know, take something like the old Apples, right? I mean, they had a programming models where basically, you you didn't deal with pointers. You had handles, and you locked those handles, and you manipulate the content. And once you unlock the handle, the OS was free to do whatever it wanted, right?
Yeah.
Then, in today's modern systems, you have the concept of transcendent memory, which again, it's RAM, right? And then that particular implementation was designed with Linux, but the interfaces that were introduced into the Linux kernel to make use of transcendent memory introduce other wonderful use cases like compressed memory, right? And again, the idea is that I have RAM, but I don't have direct access to the RAM. And sometimes, introducing these interfaces lets you write code that actually can deal with, the fact that you have relative pointers or the fact that you have compaction. It's just that, if you don't think about these things now and you start introducing programming models that people adopt, you will wind up with you sort of keep pushing away the problem until it becomes a huge issue and machines just slow down to a crawl.
Yeah, that's very good input. So let's address some of that. It's not like we're kind of pushing them away. We are in fact working on a persistent memory garbage collector, which would reduce a lot of the fragmentation issues, because if you have relative pointers, it can move things around. We are also working on relative pointers. The problem with relative pointers is that is not how your C programs work today, like I already said. So you have to sacrifice something. And I'm not saying that's a bad thing, but you have to make the programmer aware that you cannot do certain things that you may have been comfortable with. So
you sort of just have these mechanisms. I mean, these mechanisms, again, it almost seems like we keep reinventing things every 15 years. So one generation goes out, and new one comes in thinking they can solve today's problems. But what I want to say is that I think we have mechanisms today that are being adopted specifically around, transcendent memory is a bit different, right? It's basically saying, I have memory that can go away at any moment. And if you think about this is sort of interesting, right? Because it says, okay, transcendent memory is really used for caching, but then the application doesn't really assume it's always there, which brings it an interesting kind of property of recoverability, right? What happens to your lost data, right? But just the prospect of dealing with these absolute pointers that are in some root structure that gets corrupted just scares the hell out of me, actually.
yeah.
So
You'd also need new APIs to basically do relative pointers.
And you sort of do today, and it ends up being basically a key-value lookup pair, right? You have cookies, and you look this up.
That's correct.
Transcendent memory again.
Sure. Yeah. So just to be clear, there are lots of issues that let me finish up. That need to be handled, and some of the ones that I am highlighting today are kind of how you access persistent memory and how you maintain consistency. It seems like consistency is probably the stickiest issue here, and you can think about these models and say, well, even then, not all paradigms are taken care of. Like I'm talking about log-based code. There are non-blocking code, there are other concurrency paradigms. So there are a lot of issues, and this is, like I said, this is a paradigm shift, and it'll take a while for any API or any set of APIs to kind of stabilize and get adopted and so on. So, but I think it's a good time to start thinking about these, because these technologies are it's going to take 3 to 5 years for them to mature as well. So we have a few years where we can think more about these and kind of come to some common ground or a set of APIs that people can use. Yes?
Yeah, to me this to some extent seems like a solved problem, and it might be the case you have not been radical enough in your approach, because with...
Which one?
So, using your persistent memory and your APIs and such can you contrast this with, say, AS400 and the approach that they adopted?
Sorry, which one?
AS400.
You have to tell me what exactly the model is. I'm not terribly familiar with that.
So about 1970 something. Basically, they produced a single level store where the programs are referencing things through a pointer that knows what it's referencing, backed up to the database, such that the programs themselves are written without knowledge of a file system. They're searching, looking up the database.
Yeah, so there had been a bunch of work like decades back, and I guess this was one of them. Now, they really didn't succeed a whole lot. So the question is why, and that's a question we always get. So it seems like there is, because we have real hardware, or we are expecting real hardware support, we think this model can go a long way. You're right. I mean, that way it may not be totally new.
I mean, it's been commercially quite successful for the past 30, 40 years. It's
Oh,
they're
sure.
selling
I
it,
mean,
yeah.
that way, yeah. So the question is, like, how many people use that model of programming? And not many, right? And for good reasons today. So that's what I'm pointing out. So maybe we can have this discussion further offline. But yeah, let's be very clear. Right? There are a bunch of work, like I mentioned earlier, persistent programming languages that were talked about. And there were real APIs and implementations and so on. So, but to bring them into the mainstream, I think there needs to be a lot more work than what we have today. Right? So it would be wonderful to understand the trade-offs that we kind of dealt with at that point. And yeah, it was before my time, so it would be nice to understand many of those as well. So like I said, when it comes to this specific work that some of us are doing at HP, the key differentiator is that we give you kind of durability support for log-based code, which many of the other work didn't have. They required transactions. But at the end of the day, at a very high level, you are getting some kind of transactional support, quasi-transactional support for log-based code as well. So if you think about it, think about multi-thread programs that we write today. Almost everything is log-based, and wouldn't it be nice if you kind of slide a persistent region underneath that, and with no other changes to your code, you get reusable, you get basically persistent and consistent reusable data that you could come back later on, whether by the same application or by a different application that you're sharing data with, and kind of restart from where you left off pretty much. So you can reuse all the results that you computed earlier. So the goodness of this is that you're not kind of messing around with any of the isolation semantics that you already have. So if you have log-based code today, you already understand the isolation semantics. Hopefully you have dealt with or resolved any kind of concurrency errors like deadlocks and databases and so on. So like I said, you can get to persistent, consistent data pretty seamlessly. So let's see if I have quick example here. So let's talk a little bit about the semantics, and I'm not going to get through all of the slides, but let me show you the kind of code changes and semantics that we are really wanting. So let's say, how do you add to a queue today? And it could be multi-threaded. What you typically do is, let's say this is the queue that you have, and you are trying to add a new node. You allocate a node, you initialize it, and then because it's multi-threaded, you would typically hold a lock, and you would attach the node to the existing queue, and you would move the tail. So there are these two updates here where you are really changing the invariants. You're moving things around, and as you can tell, if you fail in the middle, then you have a problem. So now what if the queue is persistent? In our model, all you need to do is to turn this to a persistent memory allocator, because you are, as a programmer, you're saying, okay, all of this data is persistent, so you need to use a different allocator. And the rest of your code can remain unchanged. So, well, of course, at the outset, you would have to kind of maybe find or create a persistent region and name it and so on, set the root. But that's kind of what I called standard boilerplate code you would have to add at the outset. But when it comes to our actual algorithms, this is potentially the only change that you need to do, this kind of changes. So, and behind this, we talked a little bit about that. We have a memory allocator integrated with the garbage collector and so on, all under the hoods. And what we give you is that for this critical section, we give you an all or nothing guarantee. So without making any changes to your actual algorithms, what you get is a persistent data structure that is reusable.
The locks persistent?
You could have the locks persistent, but they don't have to be. I'm sorry?
So how do you handle the locks are persistent machine interactions process?
So basically they will be released during recovery time. So they don't have to be persistent. You could keep them transient. But if you have them persistent, then basically there will be a state change when you do a lock, right? So that will be in persistent memory. And exactly. Yeah. Well, that will be undone during recovery. So let's say if I have a slide, I think with the flow, let's move maybe later on. So what we do is this is a compiler runtime combined model. So the compiler recognizes the synchronization points, and it generates code to a runtime library. It generates calls to a runtime library. So all of the heavy lifting happens at runtime. So if there's a crash in the middle, the runtime would know, oh, I was in the middle of a critical section, which is really not consistent if you were in the middle. So it would roll back. So the runtime would automatically log all the changes that are happening within a critical section. So if your program crashes during recovery, oh, by the way, the logs are in persistent memory, so you'd be able to look at the logs, and based on what is in the logs, you could tell during recovery that there is the consistency, there are these synchronization points, and there are these logs that are held, so those would be released automatically. So all of that happens under the hoods. Let me see if I'm running out of time, so I think without going into the details, which we can talk during lunch. Okay, so this is kind of the workflow, if you will, that happens for a program. So a user program would typically use two different APIs. On the left, this is the persistent region API, which is basically having a finder, naming, setting, getting a root, and so on. On the other side is the consistency API. Now, it turns out for locking code, you basically don't have to do anything. If your synchronization is already there, you already have that. If you combine it with transactional model that I was talking about, you could have atomic sections or transactions. So you could have a combination of transactions and locks. So then that is what would go into your consistency API. So you write your user program, then you compile it with a library, with a compiler which understands some of these semantics. So that would generate calls to the runtime library. And then basically it's an instrumental user program which gets executed. It writes to persistent data. If there is a failure, then during recovery, there is a recovery code generated by the runtime as well. So that will be executed automatically, and any inconsistent state will be rolled back to a consistent one. I think more details, we already talked about that. There's an instrumentation phase that happens. Log entries get written out. The log entries are in non-volatile memory. The log is the truth. All the information is there. You can always tell by looking at the log during recovery what happened, what went wrong. You can roll back. I wanted to quickly show you some of the results that we're getting. So we took an existing database, LMDB, an open source database, which basically is a key value store originally on disks. So we adapted it to use this library, this model. So we took, so most of the work that we needed to do was kind of stripping out the existing durability layer because it was using file systems and so on. So once we did that, we put the actual databases into persistent regions, and it turns out it uses critical sections, log-based code, so basically there were no changes there. We got orders of magnitude performance improvement, and that's to be expected because we are assuming very low latencies, like DRAM-like latencies. And these are on emulated platforms. So we emulate non-volatile memory using Linux XampFS file system. So this is kind of saying that, okay, so you have today's databases or server applications using today's block-based interfaces, hard disks, and so on. If you kind of took them and with a little bit of work, hopefully, use this new model, what is the kind of performance benefit that you'd expect? Now, there are low latencies, but there are also kind of the work that I showed underneath the hoods, logging and so on, that you have to do. So the point here is that even with logging and other consistency support, you can still maintain a lot of the advantage so that you see this kind of more than 2 orders of magnitude improvement.
Question?
Yeah.
Is that percentage or multiplier?
No, so this is a speed-up multiplier. Sorry, I should have mentioned that.
168 times as fast?
Yes, yes, because we are talking about disk latencies and memory latencies. So the other one we looked at is memcached. So today it's used for cloud applications. You have this transient cache. So again, what we did is, and this has no notion of durability today. So we just used this model to convert transient memcached to a persistent memcached. So what we needed to do is basically create a persistent region and put all the cache data structures, like hash tables and various lists and so on, into the persistent container. And again, this uses critical sections, log-based code, so no change required there. And so here we are measuring the speed up. So this is the transient memcached, the original one. This is what you'd get with a library. And I didn't talk much about flush, so let's ignore that for the moment. So basically, going from transient to a durable memcached, the overhead we found was around 60%. And we're doing a bunch of gets and puts, basically, it's a key value store. So the idea is that with very little changes, can you go from a transient application to a durable one, and with hopefully very low overhead, and that's what we see today. So I think I'll just end here, kind of acknowledge that there's a lot of work to be done here. So we are kind of showing that there is a potential. There are some new class of applications that you can enable, and there are all kinds of remaining issues. This list is much longer than here: transient persistent pointers, garbage collection, other models, and also kind of embedding this notion in programming languages, which were explored years back, but we don't have today. Yeah.
Yeah, I think this is a huge subject, and we're talking to you with people, some of which
may have some sort of tangent, but we're obviously not domain experts. But like I'm sure all of us are sitting here, and little bells are going off in our mind, and we want to make comparisons. We want to ask you questions, and in some sense, this is a great topic, and I hope you will make further presentations on this. I mean, you're right. I mean, you're talking about a paradigm shift, right? So in some sense, it's not too interesting to hear about the minimum amount of changes you want to make, since we want you to introduce a new programming model, right? Yeah. I hope next time, in whatever conference or venue you make this presentation, you can make this a longer presentation, and you can start with a review of literature, because the problems that you're going to be solving, I mean, I'm pretty sure have been solved in the last 50 years. There may have been slightly different applications. People didn't have terabytes of persistent memory. Maybe it was just a small amount of memory. Maybe it was transactional memory, right? So it would really be great just, for your team to go back and actually, because now that you have identified, after doing a quick prototype, you've identified the issues, right? Or we have pointed out things that we think are an issue. So now go back in time and actually look at all these different implementations, look at all these technologies, and the next time you present, you should talk to people not about the future, but you should start in the back and say, well, this has been done, this has been done, this has been done, so people actually have a context and aren't listening to you with this doubts in their mind, like, well, I don't know about this. This way, you'll prevent a lot of questions, and then again, I think.
Well, questions are good, so.
No, I know, but it's but then the confidence level that people will have is just.
No, that's good input. It's harder to give a much longer presentation than this. The focus would have to be different, but I think that's a good idea.
You don't want to reinvent the wheel.
Many of the older technologies, many of the rethinking is not necessarily in the infrastructure support. It's in the rethinking that programmers need to do. It's the re-architecture. If you look at programs, many programs don't have any notion of persistence, and when you look at them, there is no way you can tell how they could be re-architected.
Sure, on Unix systems, on typical workstations, with a virtual address space, yes.
Yeah.
But this is not the only thing that has happened in computing history, and then it's not even the only thing that has happened today. So all I'm saying is, You're right. We're scaling out. You suddenly have memory that you can't just reboot and clear out. But that does not mean that you're inventing something new, but the technology you're using, you're probably not actually inventing. You should probably adopt. But in order to make those decisions, you should be able to list out all these achievements and technology things that have happened. So all I'm saying, next presentation, you should list those things out instead of saying, well, it was before my time, so I don't know. That's just, yes, Don Knuth is effectively before my time too, but that doesn't mean I should go and rewrite his books. I can't, effectively, right?
Yeah, that's it. Thank you. Yeah. Other questions? I think we're at lunchtime though. Yeah.
Sorry.
I think HP made an announcement recently that they didn't have production on memristors or whatever. It was delayed or forever, or I don't know what the exact statement was. Is there an alternative memory technology you're planning on using for this?
There are a number of persistent memory technologies that are being worked on in the industry. So HP and Hynix are jointly developing memristors, and it will be in a product sometime in the next few years. So there are challenges with any of these technologies, whether it's phase change, memristors, spin-top transfer RAM. So in HP discovered this year, it was announced that this we will have the machine, we'll have some prototype of the machine next year, and so on. So there are iterations of the machines that will come out, and so it will be in a product in some time. So when it comes from the software side, it really doesn't matter what exactly is the technology, because they give you pretty much the same abstractions, and the abstractions that you want: persistence and byte addressability, and with reasonable endurance and retention and so on. So if it is not memristors, the first iteration of our machine might use something else, but the memristors continue to be worked on.
There is other persistent memory technology coming out in the form, NVM form factors that you could get today, really, 8 gigs of persistent memory in a DIMM and larger. And Intel recently announced their
Crosspoint,
so
yeah.
There's stuff coming in a variety of technologies.
The long-term question, do you see that this will have a bigger implication on how we do operating systems going forward once the system becomes more mature?
I think you will. I mean, you're starting to see just the very basics. Like some code came into 4.2 to deal with NVDIMMs and primarily using them as a block device and with DAX extensions for ext4 and XFS. So I think we're just at the building block stage, and I think there'll be libraries, there'll be compiler enhancements. As Drew has been talking, there's some other works going on, but right now we're just at the enabling.
Yeah.
I mean, I don't see much difference in what you see here in the program that is today. I mean, when you say the program is stateless today, it's not really true. They're quite stateless, but there are many programs that say state on disks and such. And this is bringing another dimension, of course, of the amount of data you can save on the memory now. But the locking system and all the things you've been describing some way, I recognize that from today's problem. What I see more when I hear about that kind of memory is as well the impact of the operating system, the swap being useless, the file system being something that maybe gets completely obsolete. This kind of thing, well, maybe there won't be file, there will be objects, or it's like, I see another dimension in that technology, rather than just the locking and the things you've been describing, which I recognize from today's problems we have today's, but okay, with another dimension, another scale of the memory, maybe another speed of it, but still we lock database today, we do that today. I think there's another dimension to that which...
No, you're right. So we do many of that, but when you look, kind of pop up a level, you get durability only through databases and file systems, and there is a big difference between this model and that model, because there you have 2 formats of data, and you have a translation layer in between. So, and that creates a lot of complexity. Now, the locking is a specific example that I talked about, and I think the take-home message is more like when you go to a higher level and say, okay, so for arbitrary programs and data structures, can you identify your data that is persistent and re-architect your application so that you can come back later on and reuse that data? And also, oh, by the way, you have to keep it consistent. And how do you keep it consistent? So none of this exists today, actually. When you talk about arbitrary objects, at the object level, no one does this today.
On file today.
On files, so files are not objects, right?
Object. Well, it's a specific object, so somehow.
So that implementation is within your database. So that's where I'm saying, like, can you open this up to all the world's programmers? Like, regardless of what you're dealing with, you have this notion, you have this support available. Nothing is new when it comes to the actual details, I guess, right? So, yeah.
So I have some experience.
I can barely hear you.
Hello. Yeah. So this is a high-level question. I think I have an idea of the answer, but I don't know anything about it. So is the work on this technology driven by the wish to change the paradigm and the way program works? Or is it that it provides additional performance and the cost, or let's say the trade-off for adopting this new technology that brings additional performance is to change the paradigm, or maybe it's something between the two? So I think it's a bit related to the discussion earlier with the this having been done before, or something similar.
Yeah.
Anyway, is it just that, okay, now, today, we have an opportunity to improve performance by, again, looking at this new technology?
So both of them are there. So if you're talking about server applications where you do persist data on, let's say, disks today, you can expect a huge performance benefit. That was one of the results that I showed, because just the technology is so different. Now, but there are also potential to let's say, totally in-memory applications that you have today. Now, they're in-memory, so you're not going to get any better performance than that. But in a different way, you potentially can, because today in-memory applications, if you keep them running all the time, well, they're around. But the question is, what happens if there's a failure? In this case, there is an opportunity to store many of that intermediate data kind of very transparently, very seamlessly, and go back later on to it. So in that way, you may see performance benefit, because if you crash today, you have to start from scratch. In this model, no, you don't.
I understand that. But for example, could we have invested the same amount of work on improving so transient memory technologies to make them, let's say, much faster, and maybe hard disk technologies to make them much faster, and we would have stayed with the same model as we have today, but with faster technology here?
Well, I'm sure people are doing that, and that is going on. That will continue to go on, at least the in-memory side, because that's important. But given this new technology, this persistent memory technology, the question is, you have this already, and DRAM is not scaling, so you're going to see more and more of persistent memory. So how do you take advantage of that? That's the question.
I think I have a very naive question. This seems to be very generalized, but is anybody looking at the possibility of just replacing that entire hierarchy with NVRAM, especially for embedded systems?
Yeah, I don't know about embedded systems, but there have been research papers where people have talked about kind of converting or having the L3 cache as persistent, based on persistent memory. So yeah, there have been some research there, definitely. But I don't know of any product coming out where everything kind of is collapsed.
Right. Well, yeah. Well, like L3 is usually, I think, in a lot of chips, is still not really controlled by the OS, right? It's considered like part of DRAM.
Yeah.
But like, just like for example, with embedded devices, if the performance is good, maybe you could remove all the caches. You can take out all of the, maintenance from the OS, and then.
Right.
Like you said, the main benefit is persistence for, power management and, things like that.
Yeah, I'm not aware.
I think there are even some other people in HP, in other parts of HP, looking at things like that for embedded devices, and they're worrying about things like stray pointers, things that would normally crash the system, and then you come up fresh and life is good again. But in this case, you're not going to come up fresh. So what crashed you before could crash you again. And so how do they protect
Thank you.
Okay, should we go for lunch? Okay, thank you.